This week, we're going to continue our study of combinational logic circuit design. And the reading material is part of chapter number 4 of the Fundamentals of Digital Logic. So I'm providing the PDF on Canvas, and you guys need to read from, or the contents of these lectures are for section 4.1 to 4.5, including 4.5. And what are we going to learn? We're going to continue to go through this list, but we're going to start focusing now on K-maps. The question that we have is how to build a working circuit at the lowest possible cost. So we want to use either less gates or less ICs. So how can I do that? So this is the outline. We're going to do a quick review, then cover a little bit of all NANDs and all NORs, then go over K-mapping, and the example for the week is going to be a 7-segment display. So last week we went through the sum of products, or SOP, where we focus on getting the ones out of a truth table and write the respective terms. And we have a mathematical way of representing that. M is your minimum terms, and these are the positions or the rows where you have the ones. We also learned the product of sums, or POS, which is the opposite. Now you focus on the lines that you have the zeros, and you write the expression with those zeros. And we're talking about maximum terms, or M, and these are the rows where you have zeros. Have in mind that the rows start at 0. So 0, 1, 2, 3, 4, and 5 are going to have zeros in this case. So we call the sum of products, we call those terms minimum terms. It's the Boolean expression resulting in 1 for the output of a single cell. And for the product of sums, we call maximum terms, which corresponds to the Boolean expression resulting in 0 for the output of a single cell. So this is what we call minimum terms and maximum terms. So just again, a quick review. If we go to the lines for the POS, for example, if we go to the lines where we get the zeros, these are the maximum terms that you get out of that table. And we can put the expression in this way. So remember, we are taking these values, but we need to negate because the output is 0. And this is called product of sums, but to look as a product of sums, you need to negate all this part. You need to negate F and this one. So you need to do negation of F and negate both sides. And then just keep solving this part of the equation, applying the Morgans until you have a product of sums. And this form right now here, without simplifying, we call canonical form. All right. And from the canonical form, so as I mentioned, you either apply here the Morgans and you massage these Boolean expressions. Same thing here, finding the common terms and eliminating terms until you have something simpler. And this is what we call minimal cost function. The example here is for POS, but the same thing applies for the SOP. It's exactly the same thing, but you look at the rows where you have a 1. Alright, another way to get the POS is to look right away to those lines, and instead of negating the output, we kind of do the inverse, because it's the Morgans of what we are getting out of here. So notice that A is 0, so we write A, B is 1, we write negation of B, and C is 0, so we got C. So notice that it's the opposite, and then we, instead of having the AND gate, we use the OR. And now by taking the lines right away like this, your F is already the good one, and when you put together, you have the canonical form for your product of sums. So you don't need to apply the Morgans. You're saving a step if you know how to take the maximum terms out of the truth table. Now we have this concept of don't cares, and we'll see the importance of them when we start applying K-maps in a bit. But pretty much I can have K-maps whatever I want in our truth table. But here is just representing the don't cares as an output and how mathematically you represent that. So remember, for your SOP, we talk about minimum terms, and the don't cares now are going to be represented in line 3 and 5. So 0, 1, 2, 3, and 5. And the same thing applies for your product of sums. If your output is a don't care, you just represent with a capital D the rows where you have zeros. So the 0, the 6, and the 7. Let's go over the all NANDs and all NOR gates. The question to ask is, which circuit is simpler to fabricate? This one on the left or the one on the right? So if I count the number of transistors, I see that I have 1, 2, 3, 4 transistors on this side, and I have 6 transistors on the right. So which circuit is the one here on the left? This is a NAND gate. These are the transistors that parameterized or configured in this way so you can do an NAND. And then if I negate my NAND in front of here, if I negate, I get the AND, and it's exactly what you have over here. This is a NOT gate, so this is your NAND with a NOT gives your AND. So to produce an AND is actually more expensive in terms of transistors than producing an AND. Looking at the NORs, kind of similar thing. Over here we have 4 transistors, here we have 6. This is your NOR gate, and this is your NOR with a NOT in front of it, so I can create an OR. So the NOR is also cheaper to fabricate than the ORs. So the question is, if it's cheaper to implement or fabricate NORs and NANDs, can we implement our circuits with all NANDs and all NOR gates? Well, the answer is yes, and De Morgan says you that. If we recall De Morgan, so we can have NAND gates with 2 inputs or N inputs, the same thing for your NORs. And if you recall, your NAND in De Morgan's is the 2 theorems. Theorem 1 says that your NAND is the same thing as having an OR with the inputs negated. And the same thing applies for your ANDs. If you negate the inputs of your AND, is exactly the same thing as having an OR. So with that, if I have a sum of products, so if I look at the truth table and get all the ones, normally this is the typical circuit that you get. So a layer with ANDs and then a second layer with ORs. If I negate the line twice, I'm not changing the signal in this wire, because if the output of this AND is a 1, gets inverted on this NOT, becomes a 0, but then before enters the OR gets negated again. So if I apply this technique on both wires, now I know that these two are NANDs, and I also know by De Morgan's that this OR is the same thing as having your NAND. And here you go. A SOP can be done by using all NANDs. If I look at the product of sums, what you're doing is the first layer you're doing a bunch of OR gates that connect your second layer with ANDs, and you apply exactly the same technique. So I have a wire, and I'll kind of represent these, explain it again, but if I have a wire and I put the 1 over here, I get the 1, or if I put a 0, I get a 0. But if I go to this wire and if I negate this wire twice, if I put the 1, gets inverted to a 0 and then inverted again to a 1, and the 0 gets inverted to a 1 and then back to a 0. So notice that I'm not changing the integrity of that wire, the signal of that wire. So I can do that as long as you negate twice on that same wire. Then by doing that, now my NAND, De Morgan's, tells you that if the NAND has the input negated, becomes an OR. So any SOP can be implemented with NANDs. And how do I handle the negation, like NOT gates? Well, for example, this example that we have over here, if we want to transform this SOP as all NANDs, so notice what happened here. This OR gate, we're going to apply exactly the same thing. We negate this input and we put a NOT gate over here. So I'm not changing the integrity of this wire. And if I want this to be an AND, I do exactly the same thing. I negate this part and this one, and now you have the circuit on the bottom. This OR gate with the inputs negated becomes an AND. I know how to do NOT gates with NORs. You just short circuit the inputs, and this is already an AND. Same thing applies for your pause. If I look at the pause over here, what do I need to do? Well, if I go here to my NAND and I negate twice, and I do the same thing with this part over here, now what I have is the NORs. I short circuit the inputs of my NORs and I can do NOTs with that, and I already know that AND with two inputs negated becomes a NOR. So any SOP can be done with all NANDs, and any pause can be done with all NORs. And you can apply the technique of negating the wire twice. As long as you negate the wire twice, you can apply the technique of the NOT gates.